So here we're going to do chapter 4, sections 1 and 2, the concepts of force and mass in Newton's first law of motion. First, I'll define to you what force and mass is, and then I'll kind of show you how to apply it. And same thing with part 2 of this chapter. So beginning with force, force is defined as a push or a pull. A push can be anything like a soccer player pushing on a soccer ball, and a pull can be a water skier pulling on a rope or string that is attached to the boat. These two forces together are both called contact forces, which just means that they arise from actual physical contact between the two objects. And because we have contact forces, we can also have non-contact forces. An example of non-contact forces can be gravity pulling down on a ball. So this shows you the force of gravity, or Fg. And we can now define non-contact forces is where two objects exert forces on one another without actually touching each other. And other examples of non-contact forces can include electromagnetic forces, weak nuclear force, and also strong nuclear force. There are certain things also that you should know about force. Force is measured in what we call newtons. So later on in the chapter, you learn that force is equal to mass times acceleration, where mass is measured in kilograms and acceleration is measured in meters per second. So force is measured in kilograms times meter per second squared, which equals to newtons. Force is also a vector, so that means it has direction. So because of this, if a person is pushing a box to the right, it can have a positive force, and if a person is pushing the box to the left, it can have a negative force. But anyways, this positive and negative deal kind of depends also on your frame of reference. So now we go on to mass. Mass is defined as a property of matter that determines how difficult it is to accelerate or decelerate an object. So if we have a large object, it's going to be harder to accelerate than a smaller object. We also should know that mass is a scalar, meaning it has no direction, and mass is also measured in kilograms. Also, make sure to not confuse mass and weight. Weight is a force, specifically the force of gravity pulling down on you, or Fg, and this is measured in newtons. So here are certain scenarios with force. As I said before, force is a vector, so it has direction. So if we have certain individual forces acting on an object, you have 10 newtons to the right and 5 newtons to the left. In order to get the total force, or what is called the net force, we have to add these two forces together, keeping in mind which ones are negatives and positives. So that is the main thing when dealing with forces, or anything practically here in physics. You have to keep in mind negatives and positives when you're adding them together. So here you would have the total net force would be 10 newtons plus a negative 5, and this will then equal to 5 newtons in total. Then there are other scenarios where you'll have x and y components for your forces. So in these scenarios, you have individual forces, one pointing up 3 newtons and another pointing 4 newtons to the right. So in order to add these y and x components, you have to do Pythagorean theorem, or maybe some of you know the 3, 4, 5 triangle, special right triangle. So because of this, you know that the net force is equal to 5 newtons. And remember always to put your unit, because not a lot of people can remember that, and right now we're dealing with force, so our unit would be newtons. Okay, so because of these two concepts of force and mass, there are three laws that were developed by the scientist Isaac Newton that dealt with force and mass, and these three laws are called Newton's laws of motion. So we'll begin with the most obvious, of course, Newton's first law of motion. So Newton's first law of motion states that an object continues in a state of rest or in a state of motion at a constant velocity unless compelled to change that state by a net force. So if we have a ball in a frictionless path moving forward, then that just means that for whenever this ball will keep on going, and it will just stay on this path forever because there are no forces acting on it. Now the same thing goes with this ball being at rest. The ball, if the ball is at rest, then it will just remain there forever until a force is acting on it. Okay, so to better understand this concept, I drew a car moving forward in a frictionless path. Here the car is in constant speed, or in constant motion, therefore there are no forces acting on it right now. And because it is in constant speed and there are no forces, then that means that it has no net forces, and this also means that the car is not accelerating. And remember that a constant motion or constant speed and a constant direction is the same thing as saying constant velocity. So here I just wrote down what the definition of constant velocity is. So now we begin with inertia. Inertia is defined as the natural tendency of an object to remain at rest or in motion at a constant velocity. Inertia and mass are thought to be used interchangeably. They can be, but mass is specifically the quantitative measure of inertia. So here I did my best to draw what might look like a car and a bike. And if these two objects are, once again, sorry for the really bad drawings, but if these two objects are, like if their inertias are compared, then we can say that the car's inertia is greater than the bike's inertia. Now we go on to some concepts. So this concept specifically asks us which of the following statements can be explained by Newton's first law. When your car suddenly comes to a halt, you lunge forward, so the force is pulling you back. When your car rapidly accelerates, you are pressed backward against your seat. So now we have to pick which one shows the Newton's first law. So remember that Newton's first law states that an object in motion will stay in motion, and an object at rest will stay in rest unless a force acts on it. So because of this law, we can say that both of these statements represent this first law because they both show an object being at motion and force being applied to that object, and therefore the car, let's say in the second statement, it accelerates, or in the first statement, the car halts. So both of these statements show an object in motion and a force being acted on it. Therefore, they show Newton's first law.